now if we add a finite temperature, which we basically add a pressure gradient, force due to pressure gradient, we'll have some modification to the plasma oscillation. You can see that in the Chen's book, section 4.4. This is a little bit more general than the Chen's book. So we consider two species. So here is a continuity equation, second law of Newtonian mechanics, and the Gauss's law, and this is the closure for the system of the equation. Pretty much the adiabatic process. P equals to gamma NSTS. Gamma can be defined as the 2 plus n over n. N is the degree of degrees of freedom. So from here we can get this. You can see that from the previous videos. And here we just add another term here. As you can see, this is basically del P, grad P, and it becomes this. So since grad P, since we'll assume that the temperature is homogeneous for now, so we'll wind up having gamma Ts grad n 1s, and that's the equation we'll wind up with if you plug it in. So this will be gamma k ns ts, and then, of course I divide everything by qs n naught, so there's n naught here and q naught here. So we combine those two equations. So E1 equals to E1. We have this equation. So this is here, this is here, and we plug in the result from continuity equation. We have this here. It's nice and clean. We plug it back into make it the left hand side as omega star. Omega squared. We will have this expression, and this for the same argument as the previous video, we will consider the other species adiabatic, and we will end up left with this slightly modified plasma oscillation compared to the just normal doesn't consider the plasma oscillation doesn't consider the pressure gradient. So we have this. And just for the sake of simplicity, we'll take a notation of lambda d divided length. So then it can be expressed as omega p 1 plus gamma k squared lambda d squared. And if you plot omega versus k, then we will have something like this. I start with omega p, but as k increases, then the omega increases as well. And eventually it will go along with square root 3/2 k v thermal. You can think it as if the wavelength is sufficiently long, the computation between the thermal pressure wave compared with the electrostatic plasma wave is like two competing with each other. Once you have a long enough wavelength comparable with the thermal velocity k dot thermal velocity, then it will make the thermal characteristic more distinct.